All right, so in the last video we were trying to figure out, is it always possible to find C1 and C2 such that C1y1 plus C2y2 solves an arbitrary IVP, or an IVP with arbitrary initial conditions? What kinds of restrictions on y1 and y2 are there? And we saw that by plugging in our initial conditions, right, we could write down Cramer's rule. And in using Cramer's rule, we have a solution. We're able to solve this as long as the determinant is not zero. And so that's what we wrote down here. And then this computation again has such important meaning that we give it a name, and that name is the Wronskian. So the Wronskian of two functions, f and g, is defined to be this determinant with fg in the top, f prime g prime in the bottom. And so we just compute that. Very good. And so now I think we're ready to write down our theorem. This is theorem 3.2.3 if you're following along in the book. Theorem 3.2.3. So suppose that y1 and y2 are two solutions to our second order differential equation, our L of y equals y double prime. We'll just go ahead and write it out again here just to give you some breathing space, equals 0. Then it is possible to solve using arbitrary initial conditions y of t0 equals v0, y0, and y prime of t0 equals v0, if and only if the Wronskian of y1 and y2 at t0 is not equal to 0. Right? That's what we said. Now remember that the Wronskian, just to rewrite that, right? The Wronskian is the determinant of y1, y2, y1 prime, y2 prime, evaluated at t0, right? y1, y2 prime minus y1 prime, y2, evaluated at t0. Okay? Now, of course, the problem with using this theorem is that you kind of have to know what the t0 is, right? In order to see if your Wronskian is 0 or not. Oop, let me not put that in square brackets. That's kind of a parenthetical. Well, I can extend this a little bit, and this is 3.2.4, theorem 3.2.4. And it says that I don't really necessarily have to have the Wronskian non-zero at t naught. I only need to have, we can, let's see, how am I going to write this? Let's start with this again. Suppose y1 and y2 are two solutions to L of y equals 0. I'm just going to do a shortcut there. Then the family of solutions of the form c1y1 plus c2y2, let's call that y of t, with arbitrary coefficients, represents or includes every solution to the IVP. If and only if, or when I say IVP, right, I'm talking about the differential equation with arbitrary coefficients. And that is true if and only if there is a point t in the interval on which our solutions are defined, where the Wronskian is not 0. Okay, so in this theorem, we're saying that we needed the Wronskian not to be 0 at t naught, but this theorem actually says that you don't need it to specify t naught. As long as there is a t in our interval where the Wronskian is not 0, then we're good. Okay, now you might be saying, Well, what happens if t0 just happens to be the point where the Wronskian is 0? And then there's other points where the Wronskian is not equal to 0. Well, we're going to take care of that issue as soon as we talk about Abel's theorem. But before we get to Abel's theorem, I just wanted to do a few examples of the Wronskian just to get out of the theory for a second. So example, let's compute the Wronskian of t and t squared. So go ahead and take a moment. You might pause the video if you want. Oops, I'm writing sideways. I'm kind of sitting funny here, so my chair is squeaking and my writing is sideways. Sorry about that. T squared, 1 and 2t. 2t squared minus t squared is t squared. Okay, so you'll notice that t squared is 0 at 0 and not 0 anywhere else. And so that might be a problem with this theorem, right? So we'll look at that later. Let's just do another example first of another Wronskian maybe. I wonder if I have e to the r1t and e to the r2t, I wonder what the Wronskian is going to be. R1 e to the r1t, r2 e to the r2t. What will the Wronskian be? Let's see, that's going to be r2 times e to the r1 plus r2 times t minus r1. Good. If I rewrite that, oops, I get this expression. Now, why am I writing this? Well, remember back in 3.1, we said that if we have our ay double prime plus by prime plus cy equals 0, and we had the roots to the characteristic equation r1 and r2, and these are two distinct roots to the characteristic equation, we said that e to the r1t and e to the r2t are the two functions that we're going to be using. And this is why. Because is the Wronskian of those two functions going to be equal to 0 anywhere? Well, the exponential function is never 0. And so the only time this Wronskian would be 0 is if r1 equals r2. But can r1 equal r2? We said they could not. We said these were distinct real numbers, right? So r1 is not equal to r2. And so what we see here is that these functions, e to the r1t and e to the r2t, work to give all possible solutions, right, to our differential equation. Good. All right, with that particular a, b, and c, that's what I'm talking about. All right, so I wonder if there's a set of functions for which the Wronskian is 0. We've talked about, this is an example of one where it's sometimes 0, sometimes not. This is an example where the Wronskian is never 0. Is there an example of a set of functions where the Wronskian is always 0? And so let's try it. This is this example we want to try. Let's just try an arbitrary function f and a constant times f. And so if you take the Wronskian of f with a constant times f, what do we end up with? Well, we end up with a constant times f prime minus a constant times f prime. And what do you get? You get 0. So remember what we were saying about our theorem? Let me pull it up here real quick. Was there a restriction on y1 and y2 such that we can get every solution of the IVP written like this? Well, can y1 and y2 be constant multiples of each other? No. y1 and y2 cannot be constant multiples of each other. So somehow we have to have two functions that are different. By different, we mean the Wronskian cannot be 0. Good. All right, so I just wanted to get one more really important, oh, my foot's falling asleep. more really important. Oh gosh, yeah, I need to get some exercise after all that smoke in the air this week. Okay, I need to. What am I doing? I got a definition. Definition. Uh, if y1 and y2 are functions, are solutions, I should say, to L of y equals 0, where every or any solution can be expressed as C1y1 plus C2y2 for a particular choice of C1 and C2, then y1 and y2 are said to form a fundamental set of solutions. Good. So what you're after then, kind of a summary here, to solve the linear differential equation, we require or we need a fundamental set of solutions. Now, just as a corollary to that, we need y1 and y2 such that the Wronskian is not equal to 0, right? All right. Now, is there a way, if I have a numerical solver, I better stop. I'll start that again in the next video. I'm kind of running over time. Okay, so I'm glad we got that summary in here. So to solve our linear second-order differential equation that is homogeneous, we need a fundamental set of solutions, meaning we need to find solutions where the Wronskian is not equal to 0. Good. We'll pause here and come back for the next video.